For over a century, Einstein's theory of relativity has been the untouchable bedrock of modern physics. But what if a subtle phenomenon known as the Shapiro effect holds the key to dismantling it entirely? In 1964, Erwin Shapiro proposed what became known as the fourth test of general relativity, the Shapiro time delay. He realized that a massive object creates a gravitational well, which effectively increases the distance that light has to travel. As a light signal passes through this intense gravitational field, it takes longer to traverse the region. This delay is similar to how light slows down when passing through a dense refractive medium like water or glass. We know that the Shapiro effect causes a time delay when light passes a stationary star. But what happens when the gravitational source is moving? As the star moves between the moment the signal enters its field and when it leaves, the delay creates a velocity-dependent offset in the speed of light. This asymmetry means that light signals are deflected in the direction of the moving star. Drag from lag acts as a form of gravitomagnetic frame dragging, pulling both light and matter along with the star's motion, an unavoidable consequence of the standard delay. Special relativity's motion shift equations are founded on a critical assumption that the shape of spacetime is completely unaffected by a body's motion through it. Under this assumption, light beams travel through a fixed, rigid Minkowski geometry, and standard flat spacetime Doppler calculations apply. However, as we just established, a moving mass creates an induced asymmetry in light velocities, the Shapiro drag. This asymmetry physically deflects light beams, changing the signal's momentum and creating gravitomagnetic wavelength shifts. Flat spacetime simply cannot accommodate this. If velocity-dependent Shapiro drag exists, the core foundation of special relativity is invalidated. At this point, a textbook adherent might argue that special relativity only claims correctness where gravitational effects are insignificant, but Einstein's principle of equivalence makes every inertial mass a gravitational field source. Relativity does not allow strong gravity and weak gravity masses to obey different equations of motion. Imagine a neutron star moving relative to a small grain of sand. If they followed different rules, we could determine absolute motion, completely wrecking the concept of relativity. For motion to be relative, there must be a single, universal set of equations that applies to all masses, everywhere. If moving stars drag light, all moving matter must drag light. If special relativity is not exact for strong gravity physics, it cannot be exact for anything. This brings us to a fascinating historical question. If the Shapiro drag effect is a natural consequence of moving gravitational bodies, why wasn't it documented much earlier? Even the standard Shapiro time delay was proposed by an engineer in the 1960s rather than by theoretical physicists decades prior. As some researchers have noted, it is a mystery why Einstein did not discover this effect. One possibility is that the implications were simply too toxic to the established framework. Any form of velocity-dependent drag automatically invalidates the core assumptions of special relativity. Einstein's special theory relies on the assumption that relative motion does not alter spacetime geometry. Acknowledging Shapiro drag would have threatened the very foundation of relativistic physics. Once we accept the principle of the Shapiro time delay, the Shapiro drag effect follows inevitably. This velocity-dependent drag acts as a crucial missing piece, but it automatically invalidates special relativity. If moving gravitational bodies drag light, we can no longer rely on Einstein's fixed Minkowski spacetime. Instead, physics must evolve towards a fully dynamic geometry. We have to be prepared to rewrite the entire foundation of modern relativity theory. If you have any questions, feel free to leave them in the comments section.